Okay, so what problem were we trying to solve? We are trying to solve the problem of masses coupled to springs and acted upon by various forces, and the equation that we need is the following. So this is the most general problem we looked at. This is f sub 0. I may have just called it f last time. Doesn't matter. It's a matter of just symbols. Okay? All right. Let us first divide everything by m. Divide everything by m, then it becomes x double dot plus gamma x dot plus omega 0 square x equals f0 over m cosine omega t. I am using the fact that omega naught was defined as root of k over m. We used to call it omega, but now I'm calling it omega naught, and you should understand why I'm doing that, because there are now two omegas in the problem. There is the omega of the driving force. So you should imagine an oscillatory force grabbing this mass and moving it back and forth. Omega naught is the natural frequency of the mass. If you pull the spring and let it go, that's the frequency with which it will vibrate. There are really natural frequency which is fixed by k and m, and omega is for you to decide. You can decide to apply to it any force you like of any frequency. So first take the easy case in which the right hand side is 0. No driving force. So I'm saying let's consider the simple case f0 or f the applied force vanishes. That's the problem I spent considerable amount of time on yesterday. You can say, well, if there's no driving force, why does anything move? That's actually correct. If you took a mass and a spring and you didn't do anything to it, the solution to this equation is x equal to 0, and that's just fine. But it also has interesting non-trivial solutions, because you can pull the mass and then let it go. After you let it go, there are no forces on the system except the force of friction and the force of the spring, and that is this problem. So how do you solve this problem? I told you the way you solve this problem is you make a guess. X of t is some number a times e to the alpha t. See if it will work. And you find it will work, and you can do this in your head. I certainly don't want to repeat all of that. The reason it's going to work is that every time you take a derivative of x, you bring down an alpha and still keep e to the alpha t. So when you put that guess into this equation, you're going to get alpha square plus gamma alpha plus omega naught square times a e to the alpha t equal to 0. And if this is going to vanish, it's not because of a and it's not because of e to the alpha t, it's because this guy in brackets is going to vanish. So if that's 0, you all recognize this to be a quadratic equation. You go back to your days in the sandbox when you all knew what the answer to this is. The answer to this is minus gamma over 2 plus or minus gamma over 2 square minus omega naught square. These are the roots. Now here you have to look at, so anyway, what does this mean? This means that yes, you can find a solution to this equation that looks like a e to the alpha t. A can be any number you like. No restriction is placed on a, but alpha cannot be any number you like. Alpha has to be the solution to this quadratic equation, and there are two solutions. So you can call them alpha plus and alpha minus. That's when I branched off into two different cases. Case 1, you can see, look, when you do quadratic equations, you know the way it's going to fall out is depending on whether the stuff inside the bracket is positive or negative. So let's take the easier case when it's positive. That means gamma over 2 is bigger than omega naught. Gamma, you remember, is the force of friction. So we want it to be not only non-zero, but bigger than this amount controlled by the natural frequency. In that case, let's not go into details, But you can all see, you put whatever value you have for gamma, the square root of this is some number. The whole thing is going to be two real choices you get. One will be minus gamma over 2 plus whatever is inside the square root. Other will be minus gamma over 2 minus what you have in the square root. The only thing I want you to notice is that both these roots are negative. This guy is obviously negative because it's a minus gamma over 2 minus something else. So that's definitely negative. You may be a little worried here that this is minus gamma over 2 and this is plus something. But the plus something is smaller than the minus something because what's inside the square root is gamma over 2 square. If you took the square root of that, you will get exactly gamma over 2. But you're taking away from it this number. Therefore, this square root is smaller than this number. So the overall thing will still come out negative. So why am I so eager that it should come out negative? Why am I eager that the roots should be negative? Yes?
So when you take two derivatives, it gets the function.
No, even if I had positive, if I took two derivatives, it will work out. Yes?
Because if alpha is greater than 1, then the E won't converge to cosine.
Won't converge to what?
The cosine function.
This is not a cosine function. This is never going to be. Cosine functions related to e to the I omega t or e to the ix. These are all real exponentials. Yes?
As alpha, if alpha is positive, as t goes up, x will go to infinity.
Yeah, that's our main problem. When you write an exponential function, usually people write exponentials like this for population growth. Everyone says our problems are increasing exponentially. They always think of exponential as rising. Of course, it's also possible that if alpha were a negative number, you could write it as a times the absolute value of alpha, just to show you it's a falling exponentials. And we have a stomach only for falling exponentials. You got to think, if I pull this mass and I let it go, I expect x to go down from whatever value I had, not to keep growing indefinitely. That doesn't make any physical sense. And one of the great things about the union of mathematics and physics is the equation automatically works out that way. It gives you an answer that makes sense. Okay, so what you get then is a solution that looks like this. One number a times e to the one of the roots plus another number b times e to the other root. I wrote them, they're both e to the alpha t, but I write it as minus the absolute value so you can all see they're falling exponentials. You understand, if a number is negative, like negative 5, that can be written as the minus 1 times the absolute value of the number. So it is e to the alpha t, but I want to write it in this form. So it's falling. So this is a case where if you pull the mass and you let it go, it will just relax, eventually coming to x equal to 0, which is its normal location, equilibrium location. Now how about the numbers a and b? Right now they are completely arbitrary. And another thing you guys should know by now is how we find a and b. In order to find a and b, we need to be given more information other than simply the mass and the spring constant. They're all sitting here and the friction coefficient, but that's not enough to tell you what it does on a given day. It wants to know, well, yes, it's the mass, it's that spring, but did you pull it or did you release it in this way or that way? That's what will control the answer. They are called the initial conditions. One initial condition is, what was the value of x at time t equal to 0? That's asking you how much you pulled it when you let it go. The other initial condition is, what is the velocity, namely the derivative of x at time 0? Most of the time what you will find is you pull the mass and you release it, then it's got a non-zero x and a 0 velocity. But it doesn't have to be that way, because I could have pulled it and released it at t equal to 0, it's starting to move inwards, and that's when you jump in and you set your clocks to 0. Well, at that instant, x has a value and the velocity also has a non-zero value. They don't all have to be 0, but there are some two numbers you can pick at will. You can see that if I put t equal to 0, I'm going to get a times e to the 0, which is 1. I'm going to get a plus b is x0. That's one condition on a and b. Now take a derivative, namely find the velocity, then put t equal to 0, and set that equal to some pre-assigned number. You'll get a second equation for a and b, and we all know we can solve those two equations to find a and b. That's how you fit these free parameters to the solution tailor-made for that particular situation. You should also ask another question. Why is it that I can pick these numbers, x naught and v naught, but why not keep going? Maybe the acceleration at time 0 is some number. Why is that not up to me to decide? Can anyone tell me why that's not negotiable? Yes?
The acceleration is not a free parameter because it
Depends upon what? Can I pick the acceleration of a body at will? Yes?
F sub 0 is part of the original equation. So that tells you what the initial acceleration is.
Yeah, I'm not sure I heard the exact answer, but it sounds close enough to what I had in mind, which is Newton will tell you what the acceleration of a body is. Namely, mass times acceleration is the force, and the force, once it's given in any given problem, which is given by where the body is and what the velocity is in this example, you have no choice on what the acceleration is. But initial position and velocity are not given by Newton's law. Newton's law says if the force is so and so, the acceleration is so and so, but he doesn't tell you what should be the velocity at a given time, what should be the position at a given time. That's why they are two free numbers. That's why you have the answer with two free numbers that you can pick to bring it in accord with these two numbers. Okay, this solution to the equation with x equal to 0, from now on, I'm going to call x sub c, where c stands for the complementary function. Now, there is another thing that could have happened here, which is in fact another alternative. You can think about what I'm saying. The other alternative is when this gamma over 2 is smaller than this omega naught. Then, of course, you have the square root of a negative number. So then you go back to the stage where you're finding the root, and you say alpha equals minus gamma over 2 plus or minus square root of gamma over 2 square minus omega naught square, but that number is negative. So that can be written as a negative sign times the square root of this number. And the square root of minus 1 will come out as an I in front. So either you will get two real roots. This is a mathematical result, nothing to do with physics. A quadratic equation with real coefficients either will have two real roots, or it will have two roots which are complex conjugates of each other. You have learned the notion of complex conjugation, which is to change I to minus I. You can see the alpha plus and alpha minus have the same real part, minus gamma over 2, and have opposite imaginary parts. So in this example, alpha plus is the complex conjugate of alpha minus, and I've told you this relationship works both ways. Therefore, alpha minus is the complex conjugate of alpha plus. So what's the solution going to look like? It's going to look like A e to the minus gamma t over 2 e to the I omega prime t, but I'm going to call this fellow in brackets as omega prime. Then there's the second solution. The real part is exactly the same. Imaginary part is opposite, minus I omega prime t. Omega prime is a new frequency connected to the natural frequency and the frictional force. That's why we got three omegas. We've got to keep that in mind. Omega naught is a natural frequency vibration. If I have a driving force, I reserve the symbol omega for the frequency of the driving force. Here is yet another quantity with units of frequency, which I'm calling omega prime. So what does this guy look like? Well, first of all, it's full of complex numbers, and we don't like it. We know the oscillator should have a real coordinate. So you ask, I have not picked A and B yet. How shall I pick them so X is real? Well, forget A and B for a minute and look at this number and this number. Do you guys realize that they're complex conjugates of each other? Because I has gone to minus I. So for example, if A and B were equal numbers, this would be a real number, because number plus its conjugate, you kill the imaginary part because they have opposite imaginary parts. So A and B real is a good answer, but it's too restricted. All we will demand is that if A looks like absolute value of A times e to the I phi, B should look like absolute value of A times e to the minus I phi. In other words, B should be the complex conjugate of A. That means the same absolute value, but opposite phase. I remind you, in the complex plane, if a number z is sitting there, the complex conjugate is sitting here, they have opposite angles, phi. So if you do that, then you get A absolute value e to the minus gamma over 2 times e to the I omega prime t plus phi plus e to the minus I omega prime t plus phi. Now we have made it real. A and B both being fully real means this phi is 0, but you see phi doesn't really have to be 0. That is too much of a restriction. Phi can be whatever you like, provided the phi that A has, the phase that A has, the same as the phase that B has. That means the angle in the complex plane of the number A, the number B, have to be opposite of each other. This, you guys should know what it is. I've told you many times, this is unforgivable if you don't know what this is. E to the I theta plus e to the minus I theta over 2 is cosine theta. Since you don't have the over 2, you can write it as 2a e to the minus gamma over 2 cosine of whatever is in here, omega prime t plus phi. At this point, I'm going to change my notation a little bit in view of what's to come. Instead of calling this phi, I'm going to call it phi 0. Because another phi is going to come in, and I want to separate those two. So 2 times a is a new number. I'm going to call that c. And this is the bottom line. Answer looks like e to the minus gamma t over 2 cosine omega prime t plus phi 0. So we've done all this yesterday. I've given you the notes, but I want you to understand where we are going with all of this. If you pull a mass and let it go, it turns out there are 2 things that can happen. I really wish I had time to bring you these different masses and show you. If you have no friction, everyone knows what's going to happen. You pull the mass and let it go, it oscillates forever. In real life, there is always some friction. So let's turn on a little friction. What will happen is what's very familiar and expected. You'll start out with an amplitude of 5, go to 4, go to 3, go to 2, it'll rock back and forth, and slowly it may wiggle around, but you won't be able to see it. That's called a damped oscillation. That's really what's described by this solution. Here, it looks like a cosine of something, but the number in front of it itself is falling with time. And the picture for that will look like the following. If you just draw an exponentially falling function as your amplitude, and you multiply that by an oscillating cosine, it will do this. This is a damped oscillation. But another extreme case, which you may not think about, is if you crank up the friction more till gamma over 2 is bigger than omega naught, then what happens is, if you pull the mass and let it go, it doesn't even go to the other side of x equal to 0. It just slowly gets to 0 in infinite amount of time. You understand? If you pull it from here, you let it go, no friction is this for eternity. Small amount of friction is slowly damp the oscillation. Too much of friction, you come back slowly and you come to rest. These are the different cases, and the mathematics tells you the different cases. So that's what we like about the union of mathematics and physics. Once you wrote down the basic law of Newton, you have no choice as to where it takes you. You go where it takes, and these are the different solutions. Okay, so this was what I did earlier on in the day, but now let's go back to the more general problem I had, which is a right-hand side which is not 0. So let's write the right-hand side which is not 0, x double dot plus gamma x dot plus omega naught square x equals f naught over m cos omega t. This is called the driven oscillator. Driven oscillators are present all the time. For example, if you have a swing goes back and forth. You may choose to push the swing back and forth. If you've got a kid in a park, you're applying a force, which is an oscillating force. Whereas in the absence of external forces, all oscillations will eventually die down. Do you guys understand that? Why? Why do all oscillations die down in the absence of external forces? Yes?
Because there's internal forces of friction and air resistance.
Yeah, well, in this case, it's not air resistant, but friction. But what friction does is that in the presence of friction, you cannot prove a law of conservation of energy. We saw that. Whenever friction acts, the energy, total mechanical energy, goes down. So kinetic plus potential will decrease with time, so the oscillations get damped. But if you are pushing it from outside, you can provide a constant source of energy, so you can maintain a steady oscillation. And that's the problem we're looking at. That is this problem. So how did we solve this problem? Well, I said, I don't want to solve this equation. I'm going to manufacture another problem. Z double dot plus gamma times Z dot plus omega naught squared Z is F naught over M e to the I omega t. So let's be very clear. This is the real physics problem that occurs all the time. This is clearly not of our world, because in our world, you don't have a force e to the I omega t. All forces in the real world are real. So this is a complex force. If you break down the e to the I omega t, you all know it's cos omega t, which I like, plus I sine omega t, which I don't like. So I'm solving a problem in which on top of the force I'm really applying, that's the imaginary force put on top of it. So what is the strategy? Why are we taking the problem and making it worse than it is? Because we have a strategy. The strategy is the following. If you have right-hand side cos omega t, ask yourself what you're trying to do. You're looking for some function x of t which should obey this equation. You can try various functions. Maybe x is a cosine of time. If it's a cosine of time, two derivatives will be a cosine. No derivative will be a sine. One derivative will, no derivative will be a cosine. One derivative will be a sine. So you cannot make it into a cosine. If you took a sine, the middle guy will look like a cosine. You can try to balance that against this. The end two terms look like cosine. So neither a sine nor a cosine works. Now it turns out something in between will work. But something that always works is the following. If the right-hand side, instead of being cos omega t, was e to the I omega t, you can guess the answer immediately. Namely, z itself will behave like e to the I omega t, because then if you take two derivatives, that's going to look like e to the I omega t times some numbers. That's going to look like e to the I omega t. That's going to look like e to the I omega t. So the beauty of the exponential is that when you take derivatives, you keep getting the exponential. Okay. But now the problem is, this is not the problem. No one told you to solve this problem. But our strategy is the following. The right-hand side has got a real force and imaginary force. The real force will produce the x that I want. The imaginary force, purely imaginary, I times sin omega t, will produce a purely imaginary answer. So at the end of the day, I will find the answer and keep only the real part. That's the plan. That's going to be the strategy. So that this z, this z is going to be the x that I want, and we'll have a part hanging around y that I don't want, but y is being driven by the sin omega t, and x is being driven by the cos omega t. But now let's solve it by inspection. So let's make a guess that z looks like some number z naught e to the I omega t. Now it's very easy to take derivatives of exponential. Just pull down I omega every time you see a derivative. So z double dot will become I omega square, which is minus omega square. Z dot will become I omega, there's a gamma there, and omega naught square is just multiplying by a number. So this is what I get on the left-hand side, and I want it to equal this on the right-hand side. And you're almost there, because the time dependence of the two sides are identical, so you can cancel it. And what you find is, yes, I can satisfy the equation that's given to me, provide the number z naught, the number in front of it, obeys this condition. That's trivially solved, because we all know how to get the solution to that one. Z naught is obtained by dividing both sides by everything that multiplies z naught, which happens to be omega naught square minus omega square plus I omega gamma. So the beautiful property of the exponential function is that you take what is a differential equation and turn it into an algebraic equation. because the act of taking derivatives generally is a nasty operation. Sines become cosines, x cubed becomes 3x squared, but exponential remains the exponential. That's the property you're trying to exploit here. So now we got z naught to be this one. And z itself, the function, the complex function looking for, is f naught over m e to the I omega t divided by this quantity downstairs. This quantity downstairs I'm going to call I of omega. I of omega is a complex number. It's got a real part and an imaginary part. The real part is omega naught squared minus omega squared. Imaginary part is omega gamma. It's not a fixed complex number. At every frequency of the driving force omega, it's a different complex number. But if you're sitting at one frequency of the driving force, it's a particular number. Everyone should know how to work it out. Omega naught is root of k over m. Omega is given to you. That's some real number. Gamma is given to you. That's an imaginary part. If you actually put in numbers, it might look like 6 plus 5i. In the end, the thing I call impedance, or I, is just a complex number. But it varies from frequency to frequency. You can see that. Okay, now we got z of t. If the problem given to us was z, we're done. You don't have to do any more work. Here is the answer. But we were told to take the real part of this answer because x was the real part of the answer, y was not part of the game. How do you take the real part? Your temptation may be, well, e to the I omega t is cos omega t plus I sin omega t, so drop the I sin omega t. But that would not be right. Why is that not right? Can anyone know why that's not the way to get the real part yet? Yep. Yes? Yes. This number downstairs is not a real number. It's a complex number. So if you have a complex number on the top divided by a complex number in the bottom, the real part is not simply the real part of the top. You've got to write the whole thing so you can clearly separate the real and imaginary parts. And that's what I'm going to do next. Every complex number we know can be written as an absolute value times e to the I phi. Right? Every z looks like mod z e to the I theta because then it's mod z cos theta, which is x, plus I times mod z sin theta, which is iy. So every complex number can be written that way. And what will be the magnitude of this guy? Well, by the Pythagoras theorem, it will be the square of the real part plus the square of the imaginary part under root. Every complex number that you have will have an absolute value, which is that square plus that square under root. And it will have a phase phi, obeying the condition tan phi is the imaginary part divided by the real part. I want you to realize that in a given problem, with a given mass, given friction, given frequency, both these are known. They're simply a magnitude of I and the phase phi can be found by this process. Now write it like that. Then you get f0 over m divided by absolute value of I e to the I phi, and I got e to the I omega t on the top. I'm almost there. I'm almost there because e to the I phi in the bottom can be written as e to the minus I phi on the top. So that this whole thing becomes f0 over m divided by the absolute value of I e to the I omega t minus phi. Now it's easy to take the real part because this is cos omega t minus phi plus I sin omega t minus phi. These are all real numbers. So they'll just multiply the whole thing. But the real to imaginary separation now comes from just taking the cosine part of this exponential. And that is our final answer. That's the answer we've been looking for, which is x of t is equal to f0 over m divided by absolute value of I cosine omega t minus phi. Why did we go through the whole business of complex numbers? We went there because the answer is not a cosine and it's not a sine. Cos omega t minus phi, if you know your trigonometry, is cos omega t cos phi minus sin omega t sin phi. So it's got some cos omega t, it's got some sin omega t, and that's why it's hard to guess that answer. But if you go through complex numbers, it comes out very easily. So the next thing is to analyze the properties of the answer you got. You can write this whole thing in front as some overall amplitude x naught cosine omega t minus phi, and you ask, what does this function look like? Well, this function is obvious to all of you. It's oscillating. Notice that even though it's oscillating like a cosine, it's not in step with the applied force. The applied force is cos omega t. Its maximum occurs at 0, 2 pi, 4 pi, etc. This guy's maximum occurs somewhat later. The first maximum occurs when omega t is equal to phi. So it's said to be lagging the function. You can imagine two functions oscillating. One is behind the other one. It reaches the maximum slightly later. So the first property is, in a driven oscillator, the x will not be in step with the f. It will be lagging. Or it could be leading, depends on what phi is. Then what about the amplitude of oscillation? That's the thing that's very interesting. How big is the oscillation? It looks like f naught over m divided by the absolute value of I. Let me write the absolute value of I for you. So the amplitude of oscillation depends on the frequency. So you got to draw the graph. As a function of frequency, what does the 1 over this look like? Pardon me?
Isn't that omega 0 squared minus omega squared?
Yes, but a minus b squared and b minus a squared. That's why I've not been paying attention. Okay. Yeah, so I'm pretty careless on what I put in, but this is one occasion where I sort of know it's okay, because I'm going to square this. I don't have to remember who is omega naught and who is omega. I have to be very careful where I don't square things, like here. But if I'm squaring it, it doesn't matter. Okay, so go back here and plot something divided by this denominator and ask, what is it at various frequencies? When omega is 0, that goes away, you get omega naught squared, and omega naught squared is k over m, and I claim what you will find initially is this will become f naught over k. That will be the value of this whole amplitude at 0 frequency. I hope that makes a lot of sense to you. 0 frequency means the force is not even oscillating. It's a constant force. What x are you going to get? You're going to get the force divided by the force constant. That's the x to which you will pull the spring. That's why if you put all the omegas and masses back into proper place, you will find it's f naught over k. Then what happens is, as omega increases, this denominator, one of these guys in denominator, is starting to vanish. If gamma were a very, very tiny number, when omega naught equals omega, you will be dividing by a very small number, and the answer will have a huge rise. Then you can see when omega goes to infinity, very large omega, you're dividing by omega squared, it will fall off like this. Now, one of the homework problems is to find out exactly where it peaks. But if gamma is very small, you don't have to do much work to know it peaks at omega equal to omega naught, but otherwise it's near that. That's a phenomenon that's called resonance. Resonance is the following. You are applying a force, f naught cos omega t. You go on varying the frequency, and in response to your force, the system oscillates. The amplitude of oscillation is the largest when the applied frequency is very near the natural frequency. If you take the limit of very small gamma, this maximum is very close to omega naught. That's called resonance. If gamma is really tiny, you can get graphs where it's incredibly peaked. So that's when systems start vibrating a lot. That's why when your car goes over certain bumps, if they're periodic, they're hitting your car at a certain frequency, and if that frequency is anywhere near the natural frequency of vibration of your suspension system and the car begins to resonate. There was this famous bridge in Tacoma that was getting hit by these winds. They were coming at some frequency, and by bad luck, they coincided with the natural frequency of the bridge. So there are these famous movies made for high school in which the bridge oscillates more and more and more, then twists and turns and collapses. That's another example of resonance. People always say, yeah, I can resonate with what the person is saying. What does that mean? The person is saying whatever the hell he wants. Some people think it's interesting, and some people think it's boring. It's the same thing here. The force is acting at a certain frequency. If your natural frequency is close to that, your response is high. If it's low, you don't care. Same thing. That's mechanical systems selecting a frequency. In fact, this is how radios work. If you have a radio, if there's only one radio station, you build an electrical circuits in which the currents like to go back and forth or oscillate at a certain frequency. Radio station should send signals at that frequency. Your response will be very high. But what if there is more than one radio station, which is a fact of life? What do they do? What they do is each one sends a signal at a different frequency. You take your radio, and there are dials inside. Well, I forgot. You kids, do you know what a dial is? Okay, you are nowadays pushing some other button. There was a time when you had to turn a dial. When you turn a dial, you're changing the properties of the electrical circuit and changing its natural frequency. You move the natural frequency till it lines up with the frequency of the radio station, with one particular station. Then the response from that station is very high, and that's the sound you hear. Other stations are also present, but you are not near their maximum. They are sitting somewhere here and somewhere here. So you want the station frequency to come under this resonance peak. So if you've got a bad radio, it'll pick up sound from many stations because it's not very refined. If the peak is broad, you will get sound from many stations. So you want to build a system which is very finely sensitive to the frequency. And that requires gamma to be very small. If gamma is very, very small, you can see if gamma is going to 0, the denominator is 1 divided by 0. It's going to be infinite. So if gamma is very tiny, 1 over very tiny is very big, and you can get enormous spikes in response, and that's what people need. Okay, the last thing you need to do this problem set. By the way, I know this problem set is very nasty. Towards the end, it got tough. You got email. I agree with you that this whole course is somewhat more difficult than it has always been. Okay, I'm aware of that fact, and I will bear this fact in mind when you go into your final, because for some reason I wanted to use problems not in our book for technical reasons, so I got them from here and there or made them up. They generally tend to be more challenging and more time consuming. So if you thought this is a tough course, well, it's supposed to be a tough course, but maybe not this hard or not this time consuming. So I will remember that in the end when I make the final exam or look at your grade. I will have to compare you not simply to your predecessors, but I will have to cut you some slack and then compare you to previous generations. So this use of complex numbers is something from which I will not, however, back down. It turns out that, yes, you can do all of this without using complex numbers. Why? Because in the real world, everything has got real numbers. So you can, in fact, by orgy of trigonometric identities, solve it with sines and cosines. But eventually, I'll give you a problem where you just cannot do it in a meaningful way. The power of complex numbers is they turn differential equations into algebraic equations. All you have to do is find the roots of a quadratic equation, whereas what you started out was to find the solution of a differential equation. That advantage you will lose if you stop using complex numbers. And when you do quantum mechanics in second term, complex numbers are in the equations of motion. The analog of F equals ma, there's an I sitting there. So you cannot escape the I. It's there. So I'm saying, depending on how much exposure you had, you have to do more or less work, but you just got to get used to complex numbers. You got to get used to the absolute value, the phase angle, how to manipulate them. If you already know it, it's good. If you don't know it, you have to do more work than other people. But I'm not going to let off on that. Yes?
Should we also read up on differential equations?
No. Anything you need to know with differential equations is what I've done for you in the class today. That's it. That's the only part you know. And with complex numbers, you turned it into ordinary equations. So you have to go over these steps and work them out. That's the part I cannot do for you. That's something you have to do. All right, what is finally missing is that x of t, if I wrote for you what I wrote above, which is x naught, I don't want to write the x naught again. It's f naught over mi. Maybe I will write the whole thing, f naught over m divided by absolute value of I times cosine omega t minus phi. It turns out this is not the full answer to the question, what happens when I push a mass? Let's understand why. Suppose I go to this mass and spring system. I grab it at t equal to 0 and start shaking it. Well, at t equal to 0, x was 0 because I grabbed it at t equal to 0. Well, at t equal to 0, if I go to this solution, it's not giving me 0. It's saying it's f naught over mi cosine phi. So what happened to the freedom I had to assign the velocity and position arbitrarily? Well, it turns out that I can still do that. That's because this solution has got a part that's actually missing. And the part that's missing is this complementary solution a e to the minus gamma t over 2 cosine of omega prime t minus phi naught. You can always add the solution to this solution. Why is that? Because if x obeyed a certain equation, if I put that in, I'm saying adding this part will not change the fact it obeys the equation. Let's ask ourselves why. Go back to the top line there, f x double dot plus gamma x dot plus omega naught squared x will be equal to f naught over m cos omega t if you put this in. Now, what if you keep adding this to the solution? Will you mess it up? Imagine adding this to the left-hand side, but I claim on the left-hand side there will be no extra terms because this guy double dot plus gamma times this guy dot plus omega naught squared times this guy is 0. This is the function which you say is annihilated by the operations on the left-hand side. It's like saying the following. If you want a function whose derivative is equal to sine x, then I may say, oh, I know the function is minus cosine x, and you all know you can add to that a constant. Why do you add the constant? Why doesn't it screw up everything? Because the derivative of a constant is 0. Well, here, this is not a constant, and yet the combination of derivatives appearing in the equation act on this to give you 0. That's why you can add it without screwing up what you've done so far. So the way you do these problems is you first find this function that depends on the applied force, and you add to this solution you get for free, even in the absence of an applied force. Yes?
What does the x sub c stand for?
This is called the complementary function, and this is called the particular solution. This particular solution depends on the force, and this is the function. I don't know why it's called complement. Maybe it complements the answer, or it's a freebie and you don't pay for it with any force, but it's called complementary. But you got to add the two to get the final answer. So you will still have these numbers a and phi naught hanging around, and how do you select them? You select them if on top of it somebody tells you that this driven oscillator had a certain coordinate and certain velocity at t equal to 0. So you'll evaluate the whole expression at t equal to 0 by putting t equal to 0 everywhere. You'll get one equation involving a and phi naught, and you'll take the derivative for the velocity, set that equal to some given number. You get a second equation involving a and phi naught. You will juggle the two equations and solve for the two numbers, a and phi naught. Okay, so that is the whole story. Okay, that's what I tried to do yesterday, but this is not the first time it's happened to me that I tried to go fast. In the end, I lost time because I was not happy with the way it was explained. And I usually come back and say sorry and then do it all over again. Okay? But there's only so much I can do. The rest is up to you guys. You have to do the work, and you have to do more problems. Okay, so now we are moving off to another topic. The other topic, somebody was sighing with relief. It's not very different. Okay, these are waves. But I think it's going to be, look, I think this probably is the hardest point of what we're doing in this term, at least mathematically. Everything else we do, heat, hot water, cold water, that kind of stuff you've done in high school, that's all in your future. It's going to be a lot easier. Okay, waves. So everyone has a good feeling for waves. You go to a lake, you know, if you're a hitman for the mafia, you're dropping things in with some weight. They go down. What's the first thing they do? Once a body is falling into the water, it's carving out some body of water and diving in. So the water next to it dives in to fill that hole. But then the water even next to it dives in to fill the hole left behind by these guys. For you, it looks like a bunch of ripples traveling outwards from the center. So this is the classic example of a wave. If you've got one example, you can latch onto it every time I say wave. So what's the wave in this problem is that if I draw a plot of the height of the water versus the place where I drop the rock, or maybe I should do a top view here. If this is the top view, after a while you got these ripples emanating from this point. Or if you kept your eye next to the water, you will find these ups and downs going outwards. So the wave is some displacement of a medium. That's what people say. That's not a perfect definition because we know electromagnetic waves have no medium. They travel in vacuum. But I think for this purpose, in this course, you should imagine a wave as what happens when you excite a medium. So here's a way to think about the wave. You all understand the harmonic oscillator pretty well, right? Mass and spring system in equilibrium will sit there forever. If you give it a kick, it'll start vibrating around its equilibrium position. There you have to keep track of only one variable, x, which is the location of the mass. The wave is an oscillation of a medium. That means at every point in space there is something that's ready to oscillate. So it's not a system with 1 degree of freedom. It's a system with infinite number of degrees of freedom because the height of the water at each point is an independent variable. It can jump up and down with time. And that's what is oscillating. So if you don't do anything to the water, it'll stay at that height. But if you fiddle with it, you drop something, you hit it with something, it'll start vibrating. But except this is a vibration not of one variable, but of a variable in space and time. X was a function of time, and the name we use for the wave, if something is oscillating, such as the water measured from some point x, I'm going to use the symbol psi of x to denote the height of the water from its normal position at the point x at time t. So x is not a dynamical variable here. X labels the point. Psi is the dynamical variable. Psi is the thing jumping up and down. Okay, now there are two kinds of waves. There's the longitudinal wave and the transverse wave. And we define them as follows. The wave travels out with some velocity. So I'm going to use the symbol v for the velocity of the wave. That's something for which all of you have good intuitive understanding, so no need to mess it up right now. You go to the lake, you drop a rock, you see when the waves get to the shore, you take the distance divided by time, that's the velocity. In sound, you light up a firecracker, after a while you hear it, you can see how long it took and how far you are, and you can find the velocity. That's the velocity of sound in air. Now these velocities are all variable. Unlike the velocity of light that doesn't seem to depend on anything, all other velocities depend on various conditions. The velocity of sound depends on the temperature, for example. Or you can take the following thing. You can take an iron rod, which is made up of a lot of atoms, and you take a hammer and you hit it here. You basically compress these atoms, and they compress the atoms next to them, and the shock waves travels through this rod. That's also called sound. And that travels at a speed which is much faster than the speed of sound in air. But it's technically also called sound. If you were a creature living inside the iron bar, you will think of it as sound. Or here's another way you can hear it. For example, here's the standard example. Here's a railway track, and there is some kind of a mountain here, and you're over here, and the train is coming here. It turns out, if the train lets out a sound, the sound will travel around the bend and you will hear it. But actually, the pounding of the train on the tracks will set up shock waves in the track that you can hear by putting your ear to the track. And you will hear the train before you hear it by depending on the sound coming through the air, because the waves going through the solid travel much faster. Okay, so I would recommend that if you're going to do this, you do this somewhere here, because you won't have enough time to move if you do it here. Okay, so most of the things, please don't do this at home. This should be done by a trained person. But I certainly did it as a kid. Listen for trains before they come around the bend, and you can actually hear it the track. Or in water, if there are explosions in water, you can hear them faster if you're under the water than if you're outside the water, because the waves travel faster in water than in air. Or thunder and lightning is the most famous example. Something happens in the sky, the light gets to you first and the sound gets to you. They're traveling at different velocities. Okay, So now let's talk about longitudinal and transverse waves. When I talk to you, I think you sort of know what happens. The air in this room is at some pressure, and the pressure is constant, and the pressure is pushing your eardrum from the outside and going through your eustachian canal, pushing the drum from the inside, and the two pressures balance, and you don't feel anything. If I talk, the vocal cords move back and forth, and they increase and decrease the pressure as I talk. If I push out, I increase the pressure. If I go backwards, I decompress the air and reduce the pressure. Those shock waves propagate to your ear. They hit your eardrum, but the eardrum is getting the pressure different from the outside, but the inside pressure is fixed. So what happens is when I decompress, the eardrum comes out or it goes in. It goes back and forth, and the eardrum moves. Then behind the eardrum are the little bones, and then the bones go, and there is some tube, and there's, no, the doctors take over from this point. So some loose hair is shaking in this fluid, then it picks up some nervous things and goes to your brain. Then you figure out, you at least know what the person's saying. You're not sure why he's talking in this particular fashion, but you can at least understand and translate. So that's a long chain of transducers of energy from sound to the stuff in your ear into your brain. I draw the line at the eardrum. I don't want to go on the other side of the eardrum because very shaky turf. But this part I know very well. It's a sound wave. And it's a longitudinal wave for the following reason. If you look at the pressure waves, the molecules of air, they're going back and forth. Follow my hands. And the signal from me to you is also going from me to you. So the motion is in line with the velocity. The motion of the medium is in the same direction as the motion of the wave. A transverse wave is what you find in water if you are on a string. Take a string, clamp to that end, and you give it a little flick like that. This bump, after a while, will end up here. So the rope is moving transverse, but the velocity of the signal is to the right. So do not confuse the motion of the medium with the motion of the signal. Okay, the rope at any given point is either at rest or going up and down, but the signal is going from left to right. So the medium doesn't have to actually move in the direction of the wave. For example, if a bunch of people line up and each one tells the person next to the next person some secret, and the secret is eventually transmitted all the way to the end, what has traveled is a secret. The actual person in the first place has not gone over physically to the end. So what happens is you're sitting there, not doing anything, suddenly you hear something, you pass it on to the next person, then you've gone back to doing nothing, then the signal travels. That's what will happen in the rope here. This section of the rope is not doing anything. When this pulse hits it, it'll jump up and down for a while, then it'll quiet down, and somebody to the right will start moving. Okay, so they are the examples of longitudinal and transverse waves. So we have the notion of velocity. Now, I want to consider one concrete example of a wave, so you people have a good feeling of how to study waves in physics. So there are many, many waves, water waves, electromagnetic waves, elastic waves. I'm going to do one. I think to do one thing in some depth will give you a feeling for how you analyze waves. That's going to be waves on a string. So you have to imagine that I have a string that's been clamped at two ends, and somebody plucks the string, say, into that shape and lets it go. We know the string is going to vibrate back and forth. Let's measure a coordinate x, which is the point on the string, and psi is the displacement of the string at that point. You guys got that? This is really the x-axis. This is not my string. That is my string. Each point is labeled by an x value that it would have the string relaxed to the normal position. So we are asking, what is the displacement of the string at the point x at time t? So psi is our new dynamical variable, namely the variable for which we like to write the equations governing its motion. And we want to ask, how does psi vary with time? What will it do? If I start it out, what will it do? Do you understand the parallel to the mass and spring system? The mass and spring system, you got a mass and you got a spring. You pull the mass out to some new location. You let it go, and you want to know what it does. The answer was cos omega t. Now, at every point x, I have some string, and I displace all those degrees of freedom, and I let them go, and they're going to do something, and I want to know how they're all varying. So previously, we had only one coordinate, which I called x, which varied with time. Now at every point x, I have a coordinate psi that varies with time. And our job is to find the equation satisfied by psi. So let us take a string, and the string has to be under some tension. That means you hang some weights on the end, or you tighten it with some screws. That's the tension, so that the string is dying to break apart if you cut it. So T is the tension on the string. Without the tension, none of this will work. So here is a string. And I'm going to analyze the fate of a tiny segment of length dx. An essential parameter here is called mu, which is the mass per unit length. That means you put the string on a weighing machine, you find the mass, and you divide by the length. For example, if you got a 10-meter string and it weighs 1/10 of a kilogram, then the mass per unit length is 1/1000 kilograms per meter. And T is the tension. The textbook may use F for tension because T is the time period also. So it depends on what symbol they use in the book. I'm not completely sure. I'm going to call it T because it's been called T in the past. Now, I pull this thing, and I want to know what the whole string will do. Who is going to tell me now, what authority will decide the behavior of this string? What do we have to appeal to? Yes?
The force that returns it to the original position.
Pardon me?
The force, like in a pendulum or a spring that returns it to the original position.
Very good. So he said, find the force that will return it to the original position. And what was the it that you mentioned?
K.
Pardon me?
Force equals negative K x.
Right, but we are going to apply. Yes, any other answers before I go? Yes.
Couldn't you model the motion of the string by saying that in the middle, that by pretending that you just choosing some point in the middle of the string and being like, the motion is just the same as if we had a mass on a spring and it's oscillating back and forth from.
Yeah, it will look like that. That is correct. But all I want you to understand is there are no new laws that I'm going to invoke. I'm not going to say, well, we studied masses in spring. Today is time to study strings, and I'm going to tell you a new law of motion. There's only one law of motion. That's F equals ma. The whole purpose of my exercise now is to show you that really does control. That's why it's a super law. Everything mechanical follows from that law, and I want to show you F equals ma is all I have, and I got to use it properly. That's going to tell me what the string will do. So what I do is the string is, of course, a long and extended and complicated object. I isolate a portion of it of length dx, and I'm going to apply F equals ma to that guy. All I need to know is the F, the total force on it, and I'm going to equate it to mass times acceleration. Okay, now, this force on this little segment is the tension pulling this way, the same tension pulling that way. The tension on the string doesn't change from point to point. But the angle at which it is pulling is not necessarily the same. Here, there is some angle, theta plus delta theta, and here, there is some angle, theta. This force is at an angle, say, theta below the horizontal. This is pulling above a theta plus delta theta. So the string is curving, and therefore the tangent to the string at this end and that end are not quite the same, and that's the key. Because if they were exactly the same tension on the two ends, if you take any object like this and apply exactly the same force, they will cancel because they're opposite forces. And F is 0, ma will be 0, and this thing won't move. The reason it moves is because even though the magnitude of the force is the same, the angle at which it's acting is not the same. So I'm going to find out the vertical component of the force here and take the difference from there. So the force here will be T times sine theta plus delta theta. Theta is the angle with the horizontal. And the force on the other side will be t times sine theta. Theta is the angle made by the string from the horizontal, and that angle itself is changing over this tiny length. Next approximation, that's the force. That's going to be mass times acceleration. Mass of this little segment is the mass per unit length times the length of this segment. Now, what is the acceleration in the language of calculus? What is the acceleration here? Pardon me?
d2x over dt squared.
He said d2x over dt squared, but the d by dt squared is right. It's not d2 of x of psi, because you got to understand, I think, look, this was not fair trick, but you have to be aware that what is oscillating up and down is the coordinate psi. X is not a real dynamical coordinate. X is a label on the string. What's jumping up and down is psi. So the acceleration is the second derivative, and I write partial derivative because psi can vary with x or it can vary with time, and I want to take the second time derivative. Now come to the left-hand side, and you assume the angles involved are very small. The angles involved are very small. I remind you guys of the following identity. Sine theta begins as theta plus dot dot dot. You remember the series I wrote for you. Cosine theta is 1 minus theta square over 2. And we have decided that we are going to treat theta as so small that theta square we are not interested in. And tan theta, which is sine theta over cosine theta, is now theta over 1, which is theta. So small angle approximation is sine theta approximately equal to theta, cosine theta approximately equal to 1, tan theta may be approximately replaced by theta. So first nice break, we don't have to work with sine. We just want t of theta plus delta theta minus that, which is delta theta. Delta theta is a change in the angle from the left end of the string bit to the right end of the string bit. Now I got a dx here, so what I'm going to do is divide by a dx and multiply it by a dx. We are almost there in deriving the equation. Look, I've been calling it dx and delta x, so pardon that. Just call it just dx. Mu dx d2 psi over dt squared. Now, what is theta? I'm going to say theta is the same as tan theta in the small angle approximation. Tan theta is d psi dx. You know from the calculus, if you move horizontally by dx and you move vertically by d psi dx is the tan of the angle. That's one of the first things you learned in calculus. So this is really d by dx of d psi dx. That becomes d2 psi over dx squared equal to mu d2 psi over dt squared. Now, some of you may find the derivation hard. Then forget about the details. You're not responsible for that. But some of you may say, look, I don't ever want you to tell me something which you cannot prove, unless it's an axiom or a law of nature. Well, this is not a new law of nature, so I have to tell you where I got this. I got this by applying F equals ma to tiny portion of the string. And you can ask yourself, when you pull a string up, why does it come down? It comes down because there's a tension on the string, and the tension here and the tension here have vertical components that don't quite match. You see, if the string is flattening out like this, the vertical downward component of this is bigger than the vertical upward component of this force. If you resolve it in the vertical and horizontal part, the downward part is bigger than the upward part in this picture. Therefore, there's a net force bringing you down. The amount bringing you down is because the derivative here and here are not the same, because the derivative is the slope. So the whole thing depends on the rate of change of the rate of change, and that's why you get this. But the mass of the tiny segment also depends on dx. So dx cancels in the end. You drop it, and you get this equation. So what I want you to think of is d theta dx is really d by dx of d psi dx. And, well, I should actually use partial derivatives because psi depends on x and t. So if you're a little careful with that, you get d2 psi over dt squared. So now I'm going to write down the final wave equation. From this point on, you have to get engaged in the problem because even though you may or may not follow the derivation, you should know what is called the wave equation. This is the wave equation. d2 psi over dx square is equal to 1 over v square d2 psi over dt square, where v square is equal to t over mu, or v is square root of t over mu. I just invented a symbol v. This is very important. What you have to know is that psi, the displacement of the string at the point labeled x horizontally from the left hand at a time t, varies with time according to this equation. This is a very famous equation, and it turns out you take any elastic medium and you disturb it a little bit from equilibrium, always seems to obey equations of this type. So our job from now till some time is to analyze the equation and see what it means. What are the consequences of this wave equation? And even though I called it v, it has units of velocity. I have no right to argue that it really is the velocity of the wave. We'll have to find out. It got dimensions of velocity. You can check by putting the units in. Okay, but now let me write down a solution to this equation. Then we will understand what can happen. So this is like saying I got some equation, second derivative of x is equal to some number times x. And we said the answer is cos omega t and sin omega t. But now I got second derivative with respect to space, second derivative with respect to time, and I know that this guy is going to oscillate up and down. But it's going to oscillate. If you imagine a string, if you take a string or a water wave which is traveling back and forth, the ripples are traveling, if you took a snapshot of the wave at a given time, it will be going up and down in space. Or if you stood at one point in the water and have the wave go past you, the water will go up and down in time at a given space. You understand? If the wave is coming towards the shore, you stand in one place, you don't have to move. The wave will go past you, and where you are, the water will go up and down with time. Or if you took a picture of it at one instant, the wave will go up and down in space at a given time. So waves oscillate in space and time, and you have to guess the answer. Now, if I had more time, I can tell you guys how to deduce the answer. It's not very hard, but I just don't have that kind of time. So I'm going to just write down a solution. And in fact, there are many, many solutions to the equation. It's very general. So I'm going to write a particular solution. The solution I'm going to write down looks like this. It is some number a, which is the amplitude, and it looks like cosine some number called k times x minus omega t. Unfortunately, this k is not a force constant. It is some new symbol. And omega is another symbol whose meaning we will deduce shortly. At least you can see that I just cannot write a wave like x minus t or something, because cosine should have an argument which has no dimensions. So if I have an x, I should multiply it by some number that's got units of inverse x. And if I have a time, I should multiply by something that looks like a frequency. From dimensional analysis, I look for a solution of this form to these equations. Once again, whether you solve this, by the way, is called a partial differential equation because it involves partial derivatives. All I'm going to be content with is showing you that this solution, when I stick it into this equation, actually works. Let us first verify that it works. Then we'll come next Monday and analyze in detail what does this really do. We'll come to that in a moment. Let's verify that it works. So let's take d psi dx. What happens when you take d psi dx? When you take a partial derivative in x, it says forget about time, treat x as the only variable. Then you will get minus a sine kx minus omega t times the derivative of what's inside the argument, which happens to be k. Now if you differentiate the second time, d2 psi dx squared, you do the whole thing again, then you'll get minus a k square sine kx minus omega t. I'm sorry. Yes, thank you. Now, if you take d2 psi dt square, you will get minus omega square a cosine kx minus omega t. If you take 1 over v squared times that, you will get this. What does the wave equation say? It says the second derivative in x should be 1 over v squared times the second derivative in time. And for my solution, that's the second derivative in x, that's the second derivative in time. I want them to match. Well, they're almost there. A matches A, cos matches the cos. But omega and k are not independent numbers. Omega over v should be equal to k. In other words, this wave equation for waves on a string will have solutions that look like this, where a can be any number you like. K and omega, between the two of them, there is 1 degree of freedom. You can pick k at will and pick omega so that omega equal to kv, or pick omega freely and choose k so that k is omega over v. But there is a relation between the two of them, which you can write in any number of ways. So let us put that knowledge back into the solution. Let us say omega is in fact kv, so that we write it explicitly in terms of the k, which is completely free. So psi now looks like a cos k times x minus, now here's where you guys got to do a little mental algebra here. If I pull the k out, can you see that t will be multiplied by omega over k? But omega over k is v. So this is my solution, a cos k x minus vt. And that is a very pretty result, and I will conclude by telling you what that is telling me. It says the psi of xt, which depends on x and depends on t, depends on x and t through this combination x minus vt. In other words, if x minus vt has a certain value, psi has a certain value. If I change x and if I change t, keeping x minus vt constant, the function doesn't change, right? Because it's function only of this combination. I will argue that that really means it's the wave that's traveling at a velocity v. Let me show you why. Let's take a function e to the minus x squared. You must have seen this function in statistics. It looks like this. It likes to have x equal to 0. Take the function where x is replaced by x minus vt. Where does this function have its maximum? It has the maximum when this guy on top vanishes, that is, say, when x equal to vt. So if you took the function e to the x minus vt squared with the minus sign, at t equal to 0 it will be here, at other time it will be here, but at every instant the bump will be moving to the right, you can see with the velocity v, because the peak is at a location vt. So in a wave, the whole profile moves with the velocity, and therefore this symbol we use here is in fact the velocity of the wave. Or maybe I'll give you one extreme example. At t equal to 0, it just looks like cosine kx, and we all know what cosine kx looks like. It's got a maximum at x equal to 0. If you wait a little longer, where is this maximum? A little later. If you increase x a little bit, if you increase time a little bit, you got to increase x a little bit so that these two still cancel each other. Originally x was at 0 and t was at 0, you're at a maximum. Little later, after some time delta t, if you go to the point delta x so that these two numbers cancel, you're still writing the maximum. But that means the delta x over delta t is v. That means if you move to the right, after time delta t, you will write the crest. That means the crest is moving at the velocity v. So I think, to summarize what I've shown you so far, is that when you take a string and you have a tension on it, you pull it and let it go, it vibrates according to this equation. That's the first statement. This is a solution. I'm not telling you it's the most general one or the only one or anything. I want us to at least have one concrete solution. And I've not told you yet how to visualize the function, but I have told you whatever the function is, it is drifting to the right at a speed that we call v. Because any function of x minus vt has a property that if it did something at x equal to 0, it does the same thing at x equal to vt. That means the whole shape is bodily transported to the right. So this really signifies a wave traveling to the right. If you wanted a wave traveling to the left, you should put a plus sign here, and it will go backwards.